Lastly here, we're going to go back to the idea of looking at composition of functions when we're given formulas for those functions. So let's look at example 6 here, which looks like it'll be pretty simple. It asks me to let f of x equal x squared plus 5 and g of x equal square root of x, and then find f of g of x and state the domain. All right, so okay, we know that, f of g of x, what does that mean? That means I'm going to plug g of x in anywhere I see an x in f's function, right? But we know that g of x is the square root of x. And then the square root of x squared, well, we know that that should kind of cancel out, right, and just give me x. So we get x plus 5. So it seems like we've got this nice simple situation here where f of g of x is equal to x plus 5. Okay, so, and of course this is a line, right? This should be a line. And we know that lines don't really have domain problems, right? You can't be, when you look at y equals x plus 5, right? The kind of normal things that you would worry about in terms of restricting domains just aren't happening. So we're not, oops, hit the wrong button there. We're not too worried about that. Okay, so let's do this though. I'm going to pull up the calculator. All right, and I've taken the liberty of putting the square root of x in for y1 and x squared plus 5 in for y2. And we wanted f of g of x, right? And this was f and this was g. So what I'm going to do is I'm going to type in the composition of these functions. So the way I'm going to do that is I'm going to type y2 parentheses y3. And the way you do that is I'm going to hit vars. This will never be something I ask you to do on a test or anything, but if you may want to do it just to kind of check your work. So function vars, and then I toggled over to yvars, press enter. Then you got this list, right? So I'm going to select y2. Then I'm going to put a parenthesis here, and then do the same thing. Vars, yvars, and then, oops, y1. So you can see the kind of composition notation there, right? This was f and this was g. All right, now if I graph this, notice what we get. We do get a line like we said we should, but we kind of get half a line, right? Normally lines just cut through all x values, but this is seeming to say that the domain of this composition looks like it's from 0 onwards, right? That's what it's kind of looking like. So if I go back here, just by the graph, it would certainly seem that the domain is 0 to infinity, right? All non-negative numbers. All right, and you might already be seeing what's happening here. So just because a particular function kind of simplifies out of the process like it did here, does not mean it doesn't matter, right? Remember the picture of a composition that looks like this, right? In a composition, you have to send your x's into G first, right? And then whatever comes out gets to go into F, right? That's what a composition does. So even though you could kind of do some algebraic tricks to simplify it, and you should, that doesn't mean that you're not still technically sending it into G. So this is the domain, and we'll just note that that is because G has this domain. So the general principle that we get here is this. The domain of f of g is a set of all x in the domain of g such that g of x is in the domain of f. All right, you all followed that, right? That's not the most friendly of sentences ever written. Okay, so here's where I kind of boil it down to what it really means kind of in plain English, okay? Practically, what it means is that you can simplify your composition and exclude any x's that you need to based on that simplification, and then look at g of x, look at the inner function, and also exclude any other x values that are necessary based on that. So you're just always looking at two things, the simplified version and the inner function. So the idea is, like, on the one hand, x's are going into this big box, that's the simplified function, but on the other hand, they're also going into this little box, that's the inner function. And you got to make sure that both are okay. All right, so let's do another example where we might have to think about this. So we have f of x is equal to x minus 3, g of x equals square root of x minus 1, right? And so they want f of g of x. Okay, so that means g of x is getting put in wherever we see an x. And we know g of x is the square root of x minus 1. And down here, square root of x minus 1. And the bottom can, of course, simplify, so this will be square root of x minus 1 divided by square root of x minus 4. Okay? So what we want to do here is look at what do we know gives us trouble in something that looks like this. Well, we know that dividing by 0 is bad, right? So under the idea of can't divide by 0, it makes sense to set up the equation, well, when is that bottom going to equal 0, right? We don't want it to equal 0. Okay, so that's the square root of x not equal to 4. And then how do we solve something like this? Well, we did this back in standard 2, right? We square both sides, okay? So we get x should not be 16. And go plug 16 in here, you can see you get 4 minus 4, which is 0, which is bad, okay? So that's one thing we know. The other thing we know, though, and you can actually see it here, but also because of the inner function, right, the inner function g, we know that the domain of g, right, is what? It's 0 to infinity, right? So you can't plug negatives into a square root. And so then understand what we have to do now is we've got to pay attention to both of these things, right? It's and, right? You got to pay attention to both. So you're going to have to combine these. So start off with the interval, okay, 0 to infinity. But what we're going to do is we're going to pluck 16 right out of here, okay? So we're going to go 0 all the way until we hit 16, and we know we're not allowed to be 16, so we'll kind of interrupt ourselves at 16. And then we'll pick things back up again after 16. And so I'm accounting for, you know, the simplified version. I'm accounting for the inner function both. That's how I get an accurate domain for this composition. All right, let's do one more example here. So we have these couple of reciprocal functions. So we've got f of g of x. So f, right, is 1 over x, so this is going to be 1 over g of x. But g of x is 1 over x minus 2, so I replace g of x with 1 over x minus 2. But of course, whenever you have a fraction within a fraction, you can always feel free to take your fraction bar and turn it into division, right? So you can say 1 divided by 1 over x minus 2, which is, you know, you always multiply by the reciprocal, right? So what that means is that f of g of x equals x minus 2. All right, so going back to that principle from the previous page, we look at the end result, okay? When I look at x minus 2, I don't see any trouble, right? I can't divide by 0 when I have x minus 2. I can't take the square root of a negative when I have x minus 2, so none of the red flags come up for me. But let's check the inner function. Check the inner. Okay, well, the inner function was 1 over x minus 2, right? And we know from that that x should not be 2, right? Because that would cause us to divide by 0. So start off with the domain that's appropriate here, which would be negative infinity to infinity, but then understand that our domain is going to need to account for the fact that x can't be 2. So you're going to interrupt yourself when you hit 2 and then go 2 to infinity, because we're just plucking 2 right out of that negative infinity to infinity interval. All right, well, let's do one more here. So same functions, but let's go ahead and do the other way, right? G of f of x this time. So G of f of x. Okay, well, anywhere I see an x, right? I'm putting f of x in the function g. So this is 1 over f of x minus 2. Right? But we know that f of x is 1 over x. So I replace f of x with that. And, you know, I also don't really want to leave it this way. This isn't simplified. So I can multiply by x down here to get rid of this fraction, as long as I also do that on top. So we have x divided by 1 minus 2x. Okay, so let's remember our rule. Let's start by looking at this. Okay, just looking at the simplified version. In the simplified version here, I don't want that bottom to equal 0, right? So what I want to make sure is that 1 minus 2x is not 0. Okay, which means 1 is not equal to 2x, which means 1/2 is not equal to x. Okay, so from the simplified version of our composition, I can see that 1/2 is bad, right? So I kick it out. But I also have to think about my inner function, okay? So the inner function, okay? The inner function, of course, is f of x equals 1 over x, and it has a domain where you can't let x be 0. So again, we combine these, all right? I can't let x be 1/2 because that causes the simplified version to go haywire. I also can't let x be 0 because that causes the inner function to go badly, even though, understand, even though it looks like it would be fine here, right? But again, going back to that previous page, going up to the top here, right? We have to follow this picture. Not only does x have to work for the big function, it's got to work for the inner function too, the first one that you're sending x into. All right, so putting that all together, so we want most numbers. Most numbers are fine. So we kind of think I'm starting off with negative infinity to infinity. But I've got to interrupt myself at 0 because that's not allowed. I can pick things up after 0, and then I got to interrupt myself again at 1/2 because that's not allowed. And 1/2 to infinity. And so that is my domain.